Hello, BC Calculus students. This is Mr. Johnson, and this is the second video for section 8.7. We are on page 113, and we're looking at example 6. And in this video, we're going to look at some additional examples that carry through what we had talked about in the previous video, as well as a few other additional concepts, such as differentiation and integration with these series. So in example 6, we have a function f that's made up of a Maclaurin series that you can see in the problem. Which of the following is an expression for f of x? So one of the challenges is that even though we have cosine of x and sine of x and e to the x and 1 over 1 minus x, those four should be memorized because they're relatively common. We still have a bit of a challenge at times when we look at a problem like this and it isn't one of those four. We want to try to figure out what series expansion it actually is for, so which function it started with. Now, one of the things that is beneficial about memorizing those four is, for example, in this case, I can cross off letter A because I know that's not cosine of x. I know it's similar, but remember, cosine of x is an alternating series, and this one doesn't alternate. The other thing that I can cross off would be e to the x squared, because when we talked about this a little bit already, but e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial and so on. And if you notice the behavior of this particular one, if you were to plug in x squared for all the x's, will not produce that particular series. You're missing all the values that you would end up putting in. For example, if you put in like x squared right here, you would get x squared, but it would be divided by 1, and what you need is divided by 2 factorial. So again, you can start to eliminate some of these options. I'm just going to erase this one right now. Okay, so we're out, I think, A and E at this point. When I look at B and C, I'm looking for, negative sine of x or positive sine of x. So forget e to the x for a minute. If you're looking at sine or negative sine or positive sine, you will have some sort of alternating series embedded in the answer. And this particular one does not alternate. So I'm going to go with, I'm not going to do it fully necessarily, but I'm going to say that B and C are not what we're looking for, because I would assume if we were to expand those, they would alternate because sine alternates. So what this leads me to is basically looking at D and trying to figure out, does D actually produce this particular series? Now, I just mentioned a second ago that e to the x is 1 plus x squared, 1 plus x squared divided by 2 factorial plus x to the third divided by 3 factorial, and so on. And I don't really care too much about the general term right now. Now, if I was to take e to the x, if I was to take e to the negative x, so I was to take e to the x and I was to substitute in negative x for all the values, I would get 1 minus x plus x squared. I'm doing all the work at once here. Minus x cubed divided by 3 factorial plus x to the fourth, and so on. So what I'm doing is I am substituting in negative x for all of these x values in e to the x. That would represent e to the negative x. Now I will add these two up. So I have e to the x plus e to the negative x, which gives me, if I'm looking at each of these values, I have 1 plus 1, which is 2. I have x minus x, which is 0. I have x squared divided by 2 factorial plus x squared over 2 factorial. I'm going to write that as 2x squared over 2 factorial. My next term would be x cubed over 3 factorial minus x cubed over 3 factorial. Those would cancel. I'm left with now 2x to the fourth divided by 4 factorial, and this pattern would continue. Now, if we were to take and multiply what we just found by 1/2, that's why I didn't simplify earlier, we would get 1 plus, again, if I take this term divided by 1/2, the 2 will cancel, so I get x squared over 2 factorial plus the 2 would cancel, so x to the fourth over 4 factorial, and so on, which does map to this answer, this series, perfectly. So the answer is D, and that's how I would go about a lot of those. I would not go with A and list the terms, and then B, and then list the terms, and then C, and then list the terms, just because I think that in this case, the answer is D. You don't want to have to list out all of those. You want to try to eliminate the ones that may not be as obvious, as the answer, and then try to get down to maybe one or two that could be the answer, and then test it from there. Okay, let's move on to the next page. Okay, so on our next page, we're going to look at example number 7, and it's actually kind of a similar problem with regard to taking a series and trying to map it to a function or try to figure out which function it is. Now remember, we memorized cosine and sine, and this particular series is neither one of those. It doesn't map to either one of those perfectly. So, my next step is, okay, can I eliminate C, D, or E? And I'm not sure that I can. So for that reason, I honestly, I'm looking at C, D, and E. I think the easiest one to try is C, and that would be maybe my next go-to. So I have sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. I think if I have just a few terms, I'm going to be able to figure it out. If I divide that by x, I get 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, and that one looks like it matches perfectly. So again, sometimes it's luck of the draw. You just try the right one. In my case, D and E looked more complex, so I wanted to wait. I thought that C looked easier to try, and that happens to be the answer. Okay, let's move on to example 8. So we have a Maclaurin series for the function f given by that formula. What is the value of f of 3? So f of 3 means that our series would be from 0 to infinity, and it is negative 3 over 4 to the power of n. This is a geometric series with the first term a equal to 1, and the common ratio is negative 3/4, which is a convergent value for the geometric series. So your sum will be a, which is 1, divided by 1 minus r, so 1 plus 3/4. And if you do just a little bit of fancy algebra here, multiply by 4, you get 4 divided by 4 plus 3, and so we get a sum of 4/3. All right, let's move on to example 9. We did one really similar to this in a previous video for the section where we're looking at e to the 3x. And so when you're looking at e to the x, for example, you have it memorized, hopefully. I think this should be enough terms. We could continue, but let's just stop there. And we're looking at e to the 3x, which means that we're going to substitute in 3x for every x that you see in the original. So algebraically, we're just manipulating this to map to our correct function. Whoops, sorry, hold on. 3x cubed. All right, and then I'm just going to simplify it so it's a little bit more obvious what the answer is. So we have e to the 3x equal to 1 plus 3x plus 9x squared over 2 plus 27x cubed over 3 factorial. And they do have one more term there, but we can see that our pattern is going to be consistent with letter E. Okay, let's move on to the next page. All right, in the next, next problem, number 10, it's asking us for the sum of the series. Now remember, it used to be that when we looked at a sum of a series, it would, 9 times out of 10 would be geometric. Well, now that we have these series expansions for things like e to the x or sine of x or cosine of x, we have other ways really based on a pattern to come up with a sum. So in this case, you can see that every term has a 2 in it. There's also a hint here. Every single one of these answers has a 2 in it, which is sort of an interesting pattern. And so if you, for example, were to take and just write this out without the 2, but instead an x, you would get the following series. And this is sort of the behavior that we're trying to focus on here with regard to what's happening to this series and what it possibly can converge to. So when you think through this briefly, is this the natural log? Well, here's the deal. We don't memorize the natural log, so we don't exactly know, okay? We don't know if that's natural log. We know it's not cosine because cosine alternates. We know it's not sine, that alternates. This one looks just like e to the power of x, because remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. The general term matches. So if instead of the x value that you that we've used to try to figure out what it kind of looks like. We have 2. That means that our value, what this converges to, because the interval is infinite, would be e squared. So in other words, this is just the series expansion for e to the x, but with a 2 plugged in for x. All right, example 11, we have an integral. Now, if you think back to antiderivatives, this one would be impossible to do. We cannot use a u substitution, certainly, long division or integration by parts or anything like that. We're unable to do. You haven't seen integration by parts yet. So we could come up with an estimate for this based on a series. So for example, we know that e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. So what if we were to take a look at e to the negative x squared? So we have e to the negative x squared. That means we have 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 3 factorial, and so on. Now the general term will be negative 1 to the n times x to the 2n over n factorial. So I'm just substituting in negative x squared for each of my x's in my original e to the x function. Now we're being asked to integrate this. So let's go ahead and integrate e to the negative x. We integrate the series itself. So every term we're going to take the antiderivative, and then what we get will be x minus x cubed over 3 plus x to the 5th over, and I'm going to divide by 5, so that's going to give me 10, minus x to the 7th over 3 factorial is 6 times 7, so that's going to be over 42, and so on. Now in terms of our general term, we would have negative 1 to the n. We would do x to the 2n plus 1 divided by 2n plus 1 multiplied by n factorial. And we would continue, and ultimately we would add a c to that. So in general, and again, it's not a complete antiderivative, but in general, that would be a representation of the antiderivative of e to the negative x squared. Okay, so what we're going to do is use the first 3 terms in our next example to find the definite integral. So we're going to take the integral of this, and we're going to approximate it using the first 3 terms. So I have x minus x cubed over 3 plus x to the 5th over 10, and I'm going to evaluate from 0 to 1. This will give me 1 minus 1/3, plus 1 over 10. And then, of course, this is the upper minus the lower would be just 0. If we were to combine all of these, we would have a common denominator. So we'd have 30 over 30 minus 10 over 30 and 3 over 30. So that would give us a total of 23 divided by 30. That's going to be our approximate for that definite integral. Let's move on to the next page. Okay, example 13, we're going to talk about having trying to set up an antiderivative using a series again. Remember, sine of t to the 6th would be one that would be really difficult to do. We don't really have a skill in a technique in our class to be able to do this. So what we're going to start with is sine of x, which we know is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I think that's going to be okay for us for now. I'm going to then transition into sine of t to the 6th. So I'm going to put a t to the 6th in for every x. So I have t to the 6th minus t to the 6th cubed would be t to the 18th divided by 3 factorial plus t to the 6th to the 5th. So that would be t to the 30th divided by 5 factorial. Go back up to the original. I don't know if I just missed it or if it didn't register, but make sure to put a factorial down there. Mine was missing. Okay, and then we would of course just continue this. Okay. Now we're looking to integrate each of these terms. So I'll jump down to the bottom so it's a little bit more space. So I'm going to integrate from 0 to x, t to the 6th minus t to the 18th over 3 factorial plus t to the 30th over 5 factorial, and so on. So we get t to the 7th over 7, we're using the power rule, remember, t to the 19th divided by 19 times 3 factorial, plus t to the 31st divided by 31 times 5 factorial, and so on, and we're evaluating from 0 to x. So when we substitute in x, we get x to the 7th divided by 7 minus x to the 19th divided by 19 times 3 factorial plus, x to the 31st divided by 31 times 5 factorial, and so on. We don't have to worry about a plus c because it's a definite integral. And then, of course, this would be the upper evaluation, and then the lower would be just 0. So we end up getting, in the end, option D. Keep in mind that it's very easy to get distracted by the general term, and they're really not testing us on the general term in this problem, because if you notice, every single one of the first 3 terms in this problem is different. So we can focus our attention on those 3 terms rather than worrying about getting all messed up with the general term. But again, all the mathematics we did, we could just implement to the general term and we'd be fine. But it looks really ugly, and oftentimes people can get really distracted by that general term. Just focus on the simpler terms, just those first 3. All right, let's talk about example 14. So this is a slightly new concept. We're going to look at a limit now. And in the past, well, let's label this as just strategy 1. We would take the limit of the numerator, which is e to the x minus 1 minus x, and we get 0. Take the limit as x goes to 0 of the denominator and get 0. And we would say to ourselves, okay, our main technique here is L'Hopital's rule. So by L'Hopital's rule, we would take the limit as x goes to infinity, we would derive, as x goes to 0, we would derive the top, which is e to the x minus 1. Excuse me, we would derive the bottom, which is 2x. And from there, we would see that as x goes to 0 of the numerator, we get 0, and as x goes to 0 in the denominator, we would get 0. And we would have to do L'Hopital's again. We are certainly not, shocked by that. We've seen plenty of those problems where we have to do L'Hopital's rule twice in a row. We would have e to the x divided by 2. As x goes to 0, e to the x goes to 1, and you get an answer of 1/2. This is completely fine, by the way. This method does not disappear now that we know series. It's just that we could do this in the past, and now we have another element of, or another strategy, I should say, for indefinite limits, where we have maybe the situation where it's 0 divided by 0, and we could use L'Hopital's or possibly use series expansion. So what I'm going to do as a second technique is I'm going to use e to the x, which is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. And I'm going to look at the limit as x goes to infinity, as x goes to 0, of e to the x, which I'm going to write like this. So I'm going to make it e to the x, which is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. So that's my e to the x. I'm putting that into my limit right here. And then I'm going to subtract 1 and subtract x. So I'm going to subtract 1, subtract x, and divide by x squared. Okay, now if you think about it, our value of 1 will cancel, and our x will cancel. And so what we're left with is the limit as x goes to 0 of x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on, divided by x squared. All right, I'm going to divide each of these terms by x squared. So I'm going to take the first term divided by x squared, the second term divided by x squared, the third term, and so on. So what we get as a simplified limit is the limit as x goes to 0 of 1/2 plus x over 3 factorial plus x squared over 4 factorial, and so on. Now, if you think about it, every term from x over 3 factorial and beyond has an x in it. And if x goes to 0, that means that any term from x over 3 factorial and beyond would cancel to 0, leaving us with 1/2. So we get the same answer. I don't know which one's necessarily shorter, but I do know that they're going to require you to understand both methods, and they're going to force you into it in their own special little way. Okay, let's move on to the next page. All right, this is just a partial FRQ from 2007, so we're going to work through this one really quickly. Just parts A and B. On this one, we're going to skip the other parts for now. It says let f be the function given by e to the negative x squared. We had one just like that earlier. It says write the first 4 non-zero terms in the general term for the Taylor series for f about 0. So for part A, we're going to begin with the one that we have memorized, which is e to the x. Now I'm going to stop there because remember it says the first 4 non-zero terms. So right now I have 4 non-zero terms, and it wants the general term. It's really important that you make sure to only list what they ask for. So if you want to try to show off and say, oh, I'm going to list the first 6 terms just to show off, they figure you can't count. So that you want to make sure to follow exactly what they say. Now we're going to take negative x squared and substitute that in for x. So we have 1 minus x squared plus x to the 4th divided by 2 factorial minus x to the 6th over 3 factorial, and so on. And then I have an alternator, negative 1 to the n, x to the 2n divided by n factorial. And there we go. Those are going to be your first 4 non-zero terms in addition to your general term centered at 0 for this function f. All right, part B says that we are going to use part A. So they're forcing you into it. You cannot use L'Hopital's rule. So you're using part A to find the limit. And we can only assume that we're going to be dealt with, or that we're dealing with an indeterminate limit. So we have the limit as x goes to 0. And in the numerator, I have 1 minus x squared. Now I'm subtracting f of x. So I'm going to subtract 1. Subtract x squared, subtract x to the 4th over 2 factorial, subtract x to the 6th over 3 factorial. So notice that my signs are changing, right? Because I'm multiplying my function by negative 1. So just keep in mind that that can be a little bit confusing, okay? I'm not going to actually worry about the general term. I'm going to take all of this and divide by x to the 4th. Okay, so what we have then is the limit as x goes to 0, and we got to analyze what is left over. Now, again, we have 1 cancel, we have negative x squared cancels. So what we're left with in the numerator is negative x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on, divided by x to the 4th. So if we take a look at our limit as we simplify this, just like the other one, we're dividing every term by x to the 4th. So we have negative 1/2 plus x to the 2nd divided by 3 factorial, and so on. And remember, every term after that negative 1/2 will have an x in it. And as x goes to 0, we're left with simply just negative 1/2. Okay, let's go to the next page. Okay, we're going to attempt an entire FRQ, which is one of the first ones we've done with Taylor series and these polynomials. So we're going to look at parts A through D of this one. This one was back in 2001, and it gives us a function f given by the power series, given by the series. And we're looking for part A, the interval of convergence. Okay, remember the interval of convergence is going to come from the ratio test. So our ratio test says that we take the limit as n goes to infinity, and we have a sub n plus 1, which will be n plus 2 times x to the n times x divided by 3 to the n plus 1 times 3 times 3 to the n plus 1 divided by n plus 1 times x to the n. And this must be less than 1. So again, if you're stuck a little bit on that algebra, I'm taking this general term and I'm writing it as n plus 1 times x to the n over 3n plus 1. That's going to be my a sub n term. That's going to be here. And remember, the a sub n plus 1 term means I take n plus 1, I substitute that in. That's what I began with. And so I just am simplifying down the ratio test. We've done a lot of work with this up to this point. All right, I'm going to simplify everything down. We have a lot of cancellations. For example, x to the n cancels, 3 to the n plus 1 cancels. As n goes to infinity, n plus 2 divided by n plus 1 is going to be 1. And so this all simplifies to the absolute value of x over 3 is less than 1, which then in turn would simplify to the absolute value of x is less than 3. So the center of convergence is 0. The radius of convergence is 3. The initial interval of convergence is -3 to 3. And our next task is to test the endpoints. So we're going to test x equal to -3 in our general term. So remember, you're taking that general term that I have circled up there at the top, which is n plus 1 multiplied by x, which is going to be -3 to the n, divided by, I'm going to make 3 to the n plus 1. I'm going to make that 3 to the n times 3, because if I do, then this simplifies to -1 to the n times the quantity n plus 1 divided by 3. Now, if you notice in this case, we have just, if you get rid of the alternator for just a minute, the limit as n goes to infinity of n plus 1 over 3 is going to be infinite, which means that this particular series is going to be divergent. If we were to test, for example, x equal to 3, then we have n plus 1 times 3 to the n over 3 to the n times 3. That series gives us n plus 1 over 3, and really for the same reasons, aside from the alternator, we get divergence. All right, so the interval of convergence for part A is going to be -3 to 3, and neither one is included. It's going to be open. Okay, let's do part B, where we're going to look at the limit now. So this is going to be a connection to the last couple problems we've done. We're looking at the limit as x goes to infinity of f of x minus 1/3 divided by x. And now what I'm going to do is I'm going to utilize the series to analyze this. They don't actually specify exactly how they want us to calculate it, whether it's through the series or through L'Hopital's rule, but I'm going to go ahead and use the series. So I'm going to substitute in some of my terms for f of x in this limit. So we have f of x, we are going to then subtract that 1/3 as part of the limit. Remember, because we have the limit as f of x, the limit as x goes to infinity of f of x minus 1/3. So that minus 1/3 on the end is not part of f of x, that's just part of the limiting value. And then I divide the whole thing by x. So it looks like this. The limit, or excuse me, the 1/3 will cancel, and therefore the limit as x goes to infinity would as x goes to 0 would simplify to 2 divided by 3 squared x plus 3 over 3 cubed x squared, and so on. We would divide every one of those by x, which leads us to the limit as x goes to 0 of 2 divided by 3 squared plus 3 divided by 3 cubed x, and so on. Remember, every term after the 2/9 has an x in it, and x goes to 0, and so your limit would be 2/9 for part B. Okay, let's go ahead and continue with part C. So part C says that we want to write the first 3 non-zero terms in the general term for the infinite series that represents that definite integral. So the definite integral is from 0 to 1, and f is 1/3 plus 2 over 3 squared x plus 3 over 3 cubed x squared, and so on. Here's our general term. So again, the first three terms and the general term. Okay, our antiderivative. So the antiderivative of every part would be 1/3 x plus, now remember when you're taking the antiderivative power rule, you add 1, which is 2, and you divide by 2, which means the 2 would cancel. So we're left with x squared over 3 squared, plus, same thing, we're going to add 1 and get 3. So we have x to the third, divide by 3, so that would give you 3 cubed, and so on. And then for our nth term, we're going to add 1, which is n plus 1, and we're going to divide by that, which gives us x to the n plus 1 divided by 3 to the n plus 1, and so on. Now remember, we're evaluating this from 0 to 1, so we're not done with how we've written it so far. We have to actually substitute in 1 and then 0 and use the fundamental theorem of calculus. So we get 1/3 if x is 1 plus 1 over 3 squared plus 1 over 3 cubed, and so on. And we get 1 over 3 to the n plus 1. So there we go. There's our first three terms and our general term. Remember, we are subtracting by 0, of course, because of the fundamental theorem, but every term has an x in it, so it would be 0. So those are our first three non-zero terms and the general term. All right, for part D, our very last part, it says that we need to find the sum of the series determined in part C. So remember, the only way to really find a sum is either to compare it to one that we know, or it may be geometric. So we have a geometric series with the starting term a equal to 1/3 and r equal to 1/3 as well, because every term is being multiplied by 1/3. So the sum, which is a divided by 1 minus r, would be equal to 1/3 divided by 1 minus 1/3. And if you were to multiply by 3, you get 1 divided by 3 minus 1, and our sum in this case would be 1/2. All right, that does it for the second video for section 8.7. Thank you.